The river looks calm from the bank, a broad pane of brown glass sliding past roots and fallen branches, carrying leaves, seeds, and the fine dust of an entire forest slowly dissolving upstream. The camera hovers just above the surface as a hand enters the water for barely a second. There is no explosion, no frenzy, no cinematic swarm. There is only a sharp flash beneath the skin, a pressure like a closing zipper, and then the hand comes back out missing a precise crescent of flesh. The wound is neat, in a way that feels wrong, as if it were cut with a surgical tool rather than teeth. At first glance, it looks small, almost trivial, a shallow bite that should sting and fade. Then the blood begins to run, not in droplets, but in a steady, pulsing sheet that stains the river red for several meters downstream. This is the deception of the piranha bite. It is not the chaos people expect. It is efficiency, speed, and a level of anatomical precision that only becomes frightening once you understand what has actually been removed. Below the surface, the piranha never stops moving. Its body is compact and muscular, designed for sudden acceleration rather than long chases, with a blunt head and eyes positioned to read flashes and vibrations more than shapes. The teeth are the real weapon, triangular blades packed edge to edge in a rigid arc, self-sharpening through constant use as scales, fins, and bone wear them against one another. When the jaws close, they do not puncture, they shear. The bite removes tissue in a single clean cut, and the head often twists at the same instant, using the inertia of the body to tear free anything that resists. This combination of slicing and torsion is why piranha wounds look deceptively tidy at first, and then widen under stress. Skin is elastic, muscle fibers are aligned for contraction, and when they are cut cleanly and then pulled, they retract and split, opening pathways deep into the tissue. The river does not need dozens of bites to create serious injury. One well-placed snap can do it. From an ecological perspective, this design makes perfect sense. Piranhas are not relentless predators chasing down healthy prey in open water. They are opportunists in an environment where energy must be conserved and competition is relentless. Seasonal flooding spreads food thin across kilometers of forest, while dry periods compress life into shrinking channels where every calorie matters. A fish that can remove a chunk of tissue quickly and retreat has a massive advantage. It does not need to kill outright to feed, and it does not need to expose itself for long. In many encounters, the piranha's goal is not a full meal, but a calculated subtraction, a bite that weakens a struggling animal or capitalizes on confusion during feeding events. This is why attacks are often fast and isolated rather than prolonged. The river rewards speed, not bravado. The bleeding that follows is not an accident. Razor-sharp teeth minimize crushing, which means blood vessels are cut cleanly instead of collapsing under pressure. Clean cuts bleed more, not less, because the vessels remain open and elastic rather than being sealed by trauma. Add the twisting motion of the bite, and you get tearing along connective tissue planes that the body normally relies on to contain damage. The result is a wound that looks manageable until it refuses to stop bleeding. In warm, humid environments like the Amazon basin, this is already dangerous. Blood loss compounds shock, and shock slows the immune response, creating a cascade of vulnerability long before infection even begins. And infection is where the real clock starts ticking. Amazonian rivers are not sterile channels of flowing water. They are living soups of bacteria, fungi, protozoa, and microscopic invertebrates, all thriving in heat that rarely drops low enough to slow metabolism. Organic matter is constantly breaking down, releasing nutrients that feed microbial blooms invisible to the eye, but aggressive once they enter open tissue. A piranha bite exposes muscle, fascia, and sometimes bone directly to this environment. Unlike puncture wounds, which may seal over and trap bacteria inside, these open cuts act like sponges. Every second in the water is another infusion of organisms adapted to digest decaying flesh. The river does not care whether the tissue is attached to a living body or not. For humans, the danger is compounded by context. Most piranha injuries do not happen during dramatic encounters, but during ordinary work. A fisherman disentangling a net feels a tug and reaches in without looking. Someone wades across a shallow channel at dusk, feet shuffling through leaf litter where fish are already feeding. Hands slick with scales handle a struggling catch at the water's edge, triggering a reflex bite aimed not at the person but at motion and vibration. At night, splashes echo differently, confusing sensory cues and drawing exploratory snaps. In these moments, the piranha is not aggressive in the human sense. It is simply responding to signals that, in evolutionary terms, have always meant food. The irony is that escaping the bite itself is usually easy. The fish lets go immediately, retreating into murk and roots, its role in the encounter already complete. Panic often makes things worse than the animal ever could. Thrashing spreads the wound, increases bleeding, and keeps the injured limb submerged longer. The river keeps working while the person struggles, washing debris and microbes deeper into tissue planes that were never meant to be exposed. By the time the person reaches shore, the real damage is already underway. What follows is not dramatic in the way wildlife documentaries often promise. There is no sudden collapse, no immediate fatality. Instead, there is time, and time is dangerous. Warmth accelerates bacterial growth, while humidity slows drying and scab formation. Swelling sets in as the immune system floods the area, but that same swelling reduces circulation, limiting the delivery of immune cells and antibiotics if they are available at all. In remote regions, cleaning a wound thoroughly may be impossible. River water is the only water. Bandages are improvised. Days pass before professional care is reached, and during that window, bacteria do what evolution has trained them to do: consume exposed protein and spread along connective tissue like fire through dry grass. Understanding this changes how the piranha is seen. It is not a mindless shredder waiting to strip bodies to bone. It is a finely tuned component of a river system that recycles energy with ruthless efficiency. Its teeth are not overkill. They are perfectly matched to an environment where hesitation wastes opportunity. The danger to humans comes from misunderstanding that efficiency, from assuming that a small wound is a minor one, or that escaping the animal means the threat has passed. In reality, the bite is only the opening move in a longer ecological interaction, one that continues long after the fish has vanished into shadow. The lesson is uncomfortable because it shifts responsibility away from the animal and onto human behavior and preparation. In the Amazon, survival is often about what happens after contact, not during it. A piranha does not need to kill you to put your body under siege. It only needs to remove the barriers that normally keep the river out. From that moment on, the environment itself becomes the antagonist, relentless, invisible, and perfectly adapted to exploit weakness. Escaping the bite may feel like victory, but it is only the end of the introduction. Managing the wound is the real war, fought against heat, microbes, and time in a place where all three are always on the river's side. The water is ankle-deep and clear enough to read the ripples sliding over pale sand, a place that feels more like a shoreline than a battlefield. Sunlight fractures across the bottom in moving bands, revealing shells, drifting leaves, the faint outlines of burrows where small fish have vanished with the tide. Nothing here looks dangerous. This is the illusion that stingrays depend on, not because they intend harm, but because their entire survival strategy is built around invisibility. A ray pressed flat against the sand is not hiding so much as becoming the seabed itself, its body breathing slowly, sediment lifting and settling over its back in a rhythm so subtle it disappears into the motion of the water. The tail lies relaxed behind it, spine angled upward just enough to clear the body, not raised in threat, but ready in the way all passive defenses are ready. The step comes down directly onto the animal, and in the fraction of a second that follows, everything changes. The strike is not an attack in the predatory sense. It is a reflex triggered by pressure and proximity, a sudden contraction of muscles that whips the tail upward with extraordinary speed. The spine does not stab forward like a spear. It arcs up and back, driven by the ray's powerful tail muscles, designed to hook and rake rather than puncture cleanly. The barb is serrated with backward-facing teeth along its edges, and when it enters flesh, it carries with it a sheath of venomous tissue that ruptures on impact. The injury is over almost instantly. There is no prolonged struggle, no repeated blows. The ray bolts away in a burst of sand, vanishing into deeper water, leaving behind what looks at first like a single puncture wound, small enough to fit beneath a fingertip. Then the pain arrives, and it arrives like a system failure rather than a signal. Stingray venom is not lethal in the way people often imagine, but it is exquisitely effective at overwhelming the nervous system. The compounds disrupt sodium channels and flood nerve endings with chaos, producing pain that radiates outward from the wound in violent waves. Muscles seize. The injured limb feels as if it is burning from the inside out, while at the same time going numb in patches, the brain unable to process the conflicting signals. Swelling begins almost immediately as blood vessels dilate and tissue fills with fluid, tightening the skin and driving venom deeper into muscle compartments. This is where the clock starts, not because death is imminent, but because everything that follows becomes harder to control with each passing minute. The mechanics of the wound matter. Unlike a clean cut, a stingray injury is a puncture combined with tearing. The serrations on the spine shred tissue as it enters and again as it exits, leaving an irregular channel that collapses unevenly behind it. Sand, algae, fragments of shell, and bacteria are driven deep into the wound by the force of impact. The venom itself causes localized tissue damage, creating pockets of dead or dying cells that bacteria can colonize with ease. Cleaning such a wound thoroughly is difficult even in clinical conditions. In the shallows of a river mouth or estuary, it borders on impossible. Human behavior often makes it worse. The first instinct after being struck is to pull the foot or leg away as fast as possible, and if the spine has lodged, that movement can drag the barbs through tissue, widening the injury and leaving fragments behind. In some cases, pieces of the spine break off entirely, remaining embedded where they continue to irritate tissue and seed infection. Panic encourages people to ignore proper cleaning, to wrap the wound quickly and try to walk it off, underestimating how aggressively stingray injuries can deteriorate. Hot water immersion, which can help break down venom proteins and reduce pain, is delayed or skipped. Hours later, when swelling has doubled and redness is creeping outward, the damage is already done. From the ray's perspective, none of this is intentional cruelty. Stingrays are among the most energy-efficient large animals in shallow aquatic systems, cruising slowly over flats and river bottoms, feeding on buried invertebrates and small fish. Their flattened bodies and electroreceptive sensors allow them to detect prey hidden beneath sand, while their camouflage protects them from sharks and crocodilians above. They are not aggressive animals, and they do not pursue threats. The spine is there for one purpose only: to create enough pain and damage in a single motion to allow escape. Evolution has refined that response until it is devastatingly effective against anything that steps too close. Shallow water is where this strategy works best, and that is why humans encounter stingrays so often at the margins. Estuaries, sandbanks, tidal flats, and river mouths are biologically rich zones where nutrients concentrate and prey is abundant. They are also where people wade, fish, and work, lulled by visibility and depth into a false sense of safety. The water feels manageable, even intimate, a place where danger should be obvious and avoidable. But in these environments, the most successful animals are those that do not advertise themselves. The stingray's invisibility is its shield, and the human footstep is the trigger that turns it into a weapon. The aftermath is where the real damage accumulates. Infection sets in quietly at first, masked by swelling and pain that are already intense. Bacteria introduced at the moment of injury exploit compromised tissue, spreading along fascial planes and into muscle. In tropical and subtropical waters, these bacteria are adapted to warm temperatures and rapid growth, turning minor delays in treatment into serious complications. Abscesses form. Tissue necrosis can follow, requiring surgical debridement that removes far more than the original puncture ever did. In extreme cases, systemic infection develops, especially when wounds occur in people with underlying health issues or limited access to care. Stories of stingray injuries often focus on the moment of impact, the shock and agony of the strike, but that emphasis misses the point. The injury itself is simple. It is one spine, one reflex, one mistake. What destroys people is the cascade that follows when that injury is misunderstood or neglected. Swelling reduces mobility, making it harder to clean and monitor the wound. Pain discourages proper care, leading to shortcuts and delays. Each hour that passes allows microbes to establish themselves more deeply, transforming a defensive encounter with a fish into a prolonged medical crisis. Ecologically, the stingray remains blameless. Its role in shallow systems is vital, stirring sediment as it feeds, recycling nutrients, and controlling populations of buried invertebrates that would otherwise dominate the substrate. The same behaviors that make it essential also make it dangerous to the unprepared. There is a bitter irony in this, a reminder that risk in natural systems is rarely about malice and almost always about mismatch. Humans step into environments shaped by millions of years of evolution and expect those systems to accommodate unfamiliar bodies and behaviors. When they do not, the consequences are framed as attacks rather than collisions between incompatible rules. The lesson embedded in stingray injuries is not one of fear, but of humility. Shallow water does not mean safe water. Visibility does not mean awareness. The absence of obvious predators does not mean the absence of defenses. In these ecosystems, survival is often about reducing contact rather than winning confrontations, about understanding where not to place your weight as much as where to move. The stingray does not chase, does not stalk, does not hunt people. It waits, perfectly still, for the sand to breathe over its back, trusting that its invisibility will usually be enough. When that trust is broken by an unwary step, the outcome is swift and unforgiving. The injury happens in a blink. The pain announces itself with brutal clarity. But the true danger unfolds later, in swelling tissue and contaminated wounds, in infections that grow quietly while attention shifts elsewhere. In that sense, stingray encounters mirror the broader logic of the environments they inhabit. The moment of contact is rarely the end of the story. More often, it is the beginning of a longer struggle against forces that cannot be seen, forces that thrive on heat, moisture, and neglect. The spine does its job and is gone. What remains is a wound that demands respect, patience, and care. Ignore it, and the shallow water that seemed harmless at first will continue the work long after the ray itself has disappeared into the sand. The water closes over the surface as if nothing happened. Ripples smooth themselves out. Floating leaves drift back into loose patterns, and the night insects resume their rhythm along the bank. From above, the river erases the violence almost instantly, but beneath the skin of the person who just escaped the jaws, the damage is only beginning to declare itself. Survival stories about caimans often end at the moment the grip loosens, when the body breaks free and scrambles toward mud or reeds, lungs burning, heart hammering, alive. That moment feels like victory because it should be. Few animals in the Amazon possess jaws capable of crushing bone with the efficiency of a caiman, and fewer encounters allow a human to leave with limbs intact. But in this ecosystem, escaping the mouth is not the end of the threat. It is the point where the clock finally starts running. A caiman does not kill the way a big cat does. There is no precise targeting of arteries, no suffocating throat clamp designed to end the struggle quickly. The power of a caiman lies in brute force and leverage, in jaws built to slam shut with explosive speed and hold fast while the body twists. Teeth are conical rather than bladed, designed to puncture, pin and crush rather than slice cleanly. When those jaws close on a limb, the damage is rarely neat. Bones crack under pressure, muscle fibers rupture, and blood vessels are torn rather than cut. Even if the grip lasts only seconds, the trauma spreads outward from the contact points, radiating through tissue as shock waves of force that leave behind pockets of damage invisible from the surface. These pockets are where the real danger lives. Crushing trauma kills cells outright, depriving them of oxygen and rupturing membranes so thoroughly that recovery is impossible. What remains is dead tissue embedded within living muscle, a perfect substrate for bacteria. Unlike open wounds that bleed freely and may flush contaminants away, crushed tissue can trap blood and fluids in enclosed spaces, creating warm, oxygen-poor environments where microbes thrive. The body's immune system struggles to reach these zones effectively, especially when swelling compresses blood vessels and limits circulation. In the Amazon, where heat accelerates everything biological, this process unfolds fast. The water itself adds another layer of risk. Amazonian rivers are loaded with microorganisms adapted to break down organic matter at astonishing speed. Every fallen leaf, every drowned insect, every carcass that sinks into the silt becomes food for bacteria that specialize in decomposition. When a caiman bite opens the body, those same organisms are given immediate access to tissue that evolution never intended them to touch. Puncture wounds from teeth introduce bacteria deep into muscle, while crushing ensures that portions of that muscle are already compromised. The river does not need to be filthy to be dangerous. In these systems, life is the contaminant. Human encounters with caimans rarely involve deliberate approach. Most happen at edges, at the blurred boundary between land and water, where activities overlap. Fishing lines are checked at dusk, when light fades and silhouettes flatten. Canoes tip in narrow channels, where roots snag paddles and balance disappears. Night wading feels safer than it is because the water seems quiet, the surface unbroken, the danger hidden by darkness rather than revealed by it. Caimans hunt and rest in these same margins, drawn by fish, amphibians, and mammals that come to drink or cross. They rely on stillness and surprise, bodies aligned with current and vegetation, eyes and nostrils just above the surface, thermoregulating by absorbing warmth from water that holds heat long after the air cools. When contact happens, it is abrupt, a splash, a sudden weight, a clamp that feels less like being bitten than being caught in machinery. People who survive often do so because the caiman releases, either startled or unable to secure a better grip. In some cases, the animal is young or the angle is wrong. In others, the human body thrashes unpredictably, denying the caiman the leverage it needs to initiate a death roll. These escapes become stories told later, proof of luck, strength, or resolve. But beneath the skin, crushed tissue is already swelling, bleeding internally, and dying. Delayed medical care compounds everything. Remote river communities are often days away from hospitals equipped to handle complex trauma. Initial treatment may focus on stopping bleeding and immobilizing limbs, necessary steps that do little to address deep contamination. Antibiotics, if available at all, may not penetrate poorly perfused tissue effectively. Swelling increases pressure within muscle compartments, further strangling blood supply and creating a feedback loop of damage. Pain masks the progression of infection at first, blending into the general misery of injury until fever, redness, and foul discharge make the threat undeniable. This is where the narrative flips. The jaws are no longer the antagonist. The caiman has vanished back into the river, resuming its role as an apex opportunist in a system that demands efficiency above all else. The new enemy is time combined with biology, the slow, relentless expansion of infection fueled by dead tissue and heat. People who win the encounter in the water find themselves losing ground on land, energy drained by inflammation, sleep disrupted by pain, the body diverting resources to fight a war it was never prepared for. In severe cases, tissue necrosis spreads far beyond the original bite, requiring surgical removal that leaves lasting disability. What began as survival becomes a long recovery that reshapes livelihoods dependent on fishing, farming, or travel by water. Understanding caimans within their ecological context reframes these outcomes. They are not monsters patrolling rivers for humans. They are integral regulators of aquatic systems, controlling fish populations, scavenging carrion, and redistributing nutrients through their movements. Their physiology reflects this role. Ectothermic bodies allow them to conserve energy, basking or floating to maintain optimal temperatures while expending bursts of power only when needed. Their immune systems are remarkably robust, capable of handling wounds and infections that would be catastrophic to mammals, a reminder that what they carry without harm can devastate us. There is an uncomfortable symmetry here. The same bacteria that help recycle life in the river are what threaten humans after a caiman encounter. The same crushing efficiency that allows caimans to subdue prey quickly is what leaves behind damage that human bodies struggle to resolve. In this way, caiman injuries are less about predation and more about ecological mismatch. Humans step briefly into systems shaped by ancient pressures, interact for seconds, and then return to bodies evolved for very different environments. The consequences of that mismatch unfold over days. The phrase "dirty water" understates the reality. These rivers are biologically rich, chemically complex environments where every surface is alive. To break the skin here is to open a door into that world. When crushing trauma widens the doorway and fills it with dying tissue, the invitation becomes impossible to refuse. Infection does not arrive as an external invader so much as an inevitable continuation of the river's work, turning exposed flesh into another substrate in the cycle of decay and renewal. Survivors often describe a strange emotional arc. Relief gives way to frustration, then fear, as swelling worsens and fever sets in. The initial triumph of escape fades, replaced by the realization that the hardest part was never the encounter itself. This is the lesson the Amazon teaches repeatedly across species and habitats. Danger is rarely confined to the moment of contact. More often, it lingers in processes that are invisible, patient, and unforgiving. In the end, caiman encounters are not cautionary tales about aggression, but about aftermath. They reveal how survival in complex ecosystems depends not only on avoiding death in the instant, but on managing the biological consequences that follow injury. The jaws test strength and luck. The days after test preparation, access to care, and respect for forces that do not announce themselves dramatically. In the Amazon, you can win the moment and still lose the week, because the river never stops working, long after the surface has gone calm again. The forest floor narrows without announcing itself. A faint trail bends around buttress roots, leaf litter thins where feet have passed before, and the understory funnels movement into a corridor that feels natural to follow. Light falls unevenly here, broken by palm fronds and hanging vines, creating alternating bands of brightness and shadow that erase depth perception. This is not coincidence. In tropical forests, movement is guided by constraint, and predators that understand this geometry do not need speed. They need patience. The bushmaster waits where you must step. Unlike snakes that roam widely or pursue prey across open ground, the bushmaster's strategy is architectural. It positions itself along paths carved by animals and humans alike, places where feet land predictably and hesitation is punished by physics rather than intent. The body lies motionless among leaves, pattern dissolving into bark and rot, heat signature blended into the thermal noise of soil warmed by the day. Sensory systems tuned to vibration and chemical cues read the world without sight, mapping approach long before a foot comes down. When the strike happens, it is not reactive panic. It is execution of a plan that began hours earlier. The mechanics are fast enough to feel unreal. A coil tightens, the head launches forward, fangs drive in and out in a fraction of a second, and the snake is already withdrawing as the body recoils into cover. There is no pursuit. The bushmaster does not follow fleeing prey because it does not need to. Its venom is designed for animals that run. The bite delivers a biochemical instruction that turns movement into liability, converting exertion into accelerated damage. Pain is part of that instruction, but it is not the main message. Bushmaster venom is complex, a blend evolved to dismantle circulatory stability. Components disrupt coagulation, interfere with platelet function, and damage the lining of blood vessels themselves. In the wild, this ensures that bitten prey bleeds internally and externally, weakening rapidly as pressure drops and tissues starve for oxygen. For humans, the same mechanisms transform a localized bite into a systemic problem. Blood that should clot does not. Microbleeds accumulate, swelling increases as plasma leaks into surrounding tissue. The injury becomes less about the puncture marks and more about what is happening invisibly, minute by minute, inside the body. This delayed nature is deceptive. In the first moments after the strike, there may be little drama beyond shock and sharp pain. The bushmaster is already gone, leaving behind 2 small punctures that seem almost underwhelming given the reputation of the animal. This gap between expectation and reality is dangerous. People move, they run. They push through undergrowth or attempt long walks to reach help, unaware that every step pumps venom through muscle and lymphatic channels. Heart rate rises, circulation increases, and venom distribution accelerates. The body, in trying to save itself through exertion, spreads the threat more efficiently than the snake ever could. Decision-making under panic becomes the true battleground. Bad tourniquets are applied too tightly or too loosely, either failing to slow venom movement or cutting off blood flow entirely, compounding tissue damage and increasing the risk of limb loss. Time is wasted on improvised treatments that offer comfort rather than function. People sit and wait when they should move carefully, or they move aggressively when stillness would buy time. In remote environments, where medical care is measured in hours or days rather than minutes, these decisions matter more than the venom dose itself. The bushmaster's ecological role explains why its venom works this way. As one of the largest pit vipers in the Americas, it preys on mammals that are fast, resilient, and capable of traveling significant distances after being bitten. A venom that relied solely on immediate incapacitation would fail too often. Instead, evolution favored a formula that punishes movement and destabilizes the systems prey depend on most during escape. The snake does not need to chase because biology does the pursuit. The forest itself becomes an extension of the ambush, every step draining strength and time. Thermoregulation plays into this strategy as well. Bushmasters are largely nocturnal or crepuscular, active when temperatures drop and prey movement increases along trails. Cooler air sharpens contrast between warm bodies and the forest floor, enhancing the effectiveness of heat-sensing pits that guide strikes with astonishing precision. During the day, the snake conserves energy, coiled in refuges that maintain stable temperatures and humidity, reducing metabolic demands. This balance allows it to wait for days, even weeks, until conditions align. Patience is not a virtue here. It is a survival mechanism honed over millions of years. Human encounters often occur during moments of transition. Dusk fishing trips, early morning hikes, paths taken repeatedly without incident until familiarity dulls caution. The bushmaster does not adapt to humans. Humans adapt to routine, and routine creates predictability. The ambush corridor concept applies as much to behavior as to geography. People step where they always step, assume safety based on past success, and underestimate how little margin exists between normal movement and catastrophic contact. When the bite occurs, the body's internal clock resets. Coagulation pathways falter, swelling increases, and pain intensifies in waves that sap focus and judgment. Nausea, dizziness, and weakness follow as blood pressure fluctuates. In some cases, bleeding from gums or wounds elsewhere signals systemic involvement. These are not immediate theatrics, but slow confirmations that the venom is doing its work. The danger grows in proportion to delay, and delay is often driven by confusion rather than ignorance. There is a cruel irony in how survivable many bushmaster bites can be with prompt, correct action. Anti-venom exists. Supportive care can stabilize coagulation and limit tissue damage. Immobilization, calm and efficient transport save lives and limbs. Yet the environments where bushmasters live are often those where such care is hardest to reach. The forest that shapes the snake's strategy also shapes the human response, imposing distance, fatigue, and uncertainty. In these settings, the difference between survival and tragedy is rarely bravery. It is clarity. The bushmaster itself fades quickly from the narrative. After the strike, it resumes stillness, conserving venom, resetting its trap. It does not watch the outcome, because outcomes are irrelevant to its strategy. The snake's success is measured in probabilities, not guarantees. Enough prey will succumb, enough bites will feed the cycle. The forest does not require perfection, only persistence. For humans, the lesson is stark. The strike is seconds, but the consequences are hours, sometimes days, of physiological negotiation. The real test begins after the fangs withdraw, when panic threatens to dictate action, and every decision either slows or accelerates the internal cascade set in motion. Understanding this reframes fear into respect. The bushmaster is not a roaming executioner. It is a specialist in waiting, a master of constraint, a reminder that in dense ecosystems, danger is often positioned, not pursuing. To walk these forests safely is not to eliminate risk, but to recognize where choice exists. Step placement, pace, response to injury, and prioritization of care all matter more than luck once contact is made. The bushmaster teaches this with brutal efficiency. Its ambush is silent, its venom subtle in its timing, its consequences drawn out long enough to reveal every mistake. In the end, survival is less about enduring pain than about managing time, because in the hours after the bite, the forest is still watching, indifferent, while biology decides how the story ends. The contact is so light it barely registers as an event. A forearm brushes a leaf while pushing through undergrowth, fingers steadying against a branch slick with humidity, skin grazing something soft and harmless looking. There is no bite, no sting, no sudden violence to warn that anything has gone wrong. The forest does not react. Birds continue calling, insects hum, and the path ahead looks exactly as it did a second before. This is how venomous caterpillars work. The trigger is not aggression or defense in motion, but proximity. You do not get attacked, you activate them. On the underside of the leaf, pressed along a midrib or stretched lengthwise like a fragment of moss, the caterpillar remains still. Its body is armored not with plates or spines in the way mammals instinctively recognize as dangerous, but with thousands of microscopic hairs, each one hollow, brittle, and packed with toxin. These structures are not designed to inject venom in a single burst. They are designed to break. When skin touches them, even lightly, the tips snap off and embed themselves like glass fibers, anchoring toxin directly into the upper layers of tissue. The caterpillar does not move. It does not flee or strike. It simply continues being what it is, while the injury unfolds somewhere else. The sensation at first can be misleading. There may be a faint itching, a tingling warmth that feels like an insect crawl, or a mild irritation from plant sap. In a humid jungle, where sweat runs constantly and minor abrasions are routine, such signals are easy to ignore. People wipe their arms. They scratch absent-mindedly. They smear sweat, dirt, and whatever is on their skin across a wider area. Each of those actions drives more hairs deeper or transfers them to new contact points. The clock has started, not because the venom is fast, but because it is persistent. Venomous caterpillar toxins vary by species, but many share a strategy built around inflammation and tissue disruption rather than immediate incapacitation. Some compounds trigger massive histamine release, causing swelling and redness that spread well beyond the initial contact zone. Others interfere with blood clotting or damage small blood vessels, leading to bruising and, in severe cases, bleeding beneath the skin. Pain escalates as nerve endings become sensitized, shifting from itch to burn to a deep, throbbing ache that radiates outward. Because the spines remain embedded, toxin delivery continues over time, turning a momentary brush into a prolonged exposure. This delayed escalation is what makes these encounters so dangerous in everyday jungle life. People are rarely stationary when they make contact. Harvesting crops, clearing trails, collecting firewood, or simply walking between villages involves constant brushing against vegetation. Children grab leaves and branches instinctively, their smaller bodies bringing faces and hands into contact with areas adults might miss. Sweat complicates everything, dissolving toxins and carrying them across skin, into eyes, onto necks and torsos. By the time pain demands attention, the exposure has often expanded far beyond the original touch. Ecologically, this system is elegant. Caterpillars are slow, soft-bodied, and rich in nutrients. Exactly the kind of prey that would be annihilated quickly in a forest full of birds, reptiles, and mammals. Venomous hairs shift the cost-benefit equation. Predators that attempt to eat or even investigate these larvae learn quickly that contact comes with consequences. Pain, irritation, and in some cases systemic illness create a powerful deterrent that does not require the caterpillar to fight or flee. Bright colors or unusual textures amplify the message, reinforcing avoidance after a single bad encounter. The caterpillar survives not by escaping danger, but by making itself expensive to touch. For humans, the weirdness lies in how impersonal the injury feels. There is no antagonist to point to, no moment of clear cause and effect. The leaf looks ordinary. The caterpillar, if noticed at all, seems inert, even fragile. Yet hours later, the arm is swollen, skin tight and angry, pain pulsing with a rhythm that disrupts sleep and focus. In severe cases, nausea, headache, or generalized weakness appear, signs that toxins have moved beyond the skin into broader physiological systems. The forest has poisoned you without moving, without announcing itself, without breaking the calm of the scene. Scratching accelerates the damage. Embedded hairs fracture further, releasing more toxin and creating additional micro-injuries that invite secondary infection. In tropical conditions, bacteria seize these opportunities quickly. What began as envenomation becomes a combined assault of toxin and infection, each amplifying inflammation and delaying healing. Folk remedies and improvised treatments often worsen the situation, grinding hairs deeper or spreading them across new areas. The instinct to wash aggressively with river water introduces yet another layer of microbial risk. Children are especially vulnerable, not only because of curiosity, but because of scale. A contact area that is trivial on an adult arm represents a larger proportion of a child's body surface. Toxin dose relative to body mass increases and symptoms escalate faster. Stories circulate in jungle communities of children hospitalized after playing with furry leaves, a phrase that captures both the innocence of the trigger and the severity of the outcome. These are not rare anomalies. They are predictable consequences of living in a system where defenses are designed for creatures that touch without thinking. The caterpillar's life cycle adds another layer of complexity. Many venomous species cluster during certain seasons, their numbers swelling as host plants flush with new growth. Outbreaks coincide with agricultural cycles, increasing the likelihood of human contact precisely when people are working most intensely in vegetation. After metamorphosis, the danger vanishes, leaving behind no obvious trace that the environment has changed. 1 week, a path is safe. The next, it is lined with invisible needles waiting for skin. Understanding the biology reframes fear into awareness. Venomous caterpillars are not anomalies or freak hazards. They are integral parts of forest food webs, converting plant matter into biomass while defending themselves with chemistry rather than speed. Their toxins are products of evolutionary arms races, refined to exploit the physiology of vertebrate predators. That humans suffer from them is incidental, a byproduct of overlapping spaces rather than targeted hostility. The clock in these encounters is subtle. It is not the rapid countdown of a snakebite or the immediate trauma of a large animal attack. It is the slow accumulation of exposure, the compounding effects of scratching, sweating, and delay. Early recognition matters. Removing embedded hairs carefully, avoiding friction, and managing inflammation can dramatically alter outcomes. But recognition requires knowledge, and knowledge competes with routine, fatigue, and the assumption that danger announces itself loudly. This is the unsettling lesson venomous caterpillars deliver. In the rainforest, harm does not always come from teeth, claws, or sudden movement. Sometimes it comes from stillness, from defenses that wait passively for contact, and then let biology do the rest. The forest does not need to chase you, corner you, or even notice you. It only needs you to touch the wrong thing while going about your day. By the time pain peaks, the caterpillar is long forgotten, still clinging to its leaf, or already transformed into something else entirely. The injury feels personal, but it is not. It is ecological, the result of intersecting lives shaped by different pressures and priorities. The forest can poison you without moving, and that truth is not meant to inspire fear so much as respect. In environments this complex, danger is often woven into the fabric of normalcy, waiting not for confrontation, but for contact. The forest trunk looks solid, dependable, a vertical anchor in a world of shifting footing and wet leaves. Bark flakes under the palm as weight leans in for balance, fingers curling around lianas that hang like ropes from the canopy. Nothing moves at first. The ants are already there, but stillness is part of their defense. Then the pain detonates, not gradually, not as warning, but as a full neurological event that hijacks the body before the mind can process what happened. This is the bullet ant's weapon. It does not wound tissue in any meaningful way. It assaults decision-making itself. The sting is delivered by a single ant, large by ant standards, armored, deliberate. The mandibles clamp, anchoring the body, and the stinger drives in with precision. The venom is injected deep, not sprayed or smeared, and its effect is immediate and overwhelming. Pain erupts as a pure signal, sharp and electric, radiating outward from the point of contact and flooding the nervous system. Muscles spasm, breath catches, vision narrows. This is not pain meant to teach caution over time. It is pain meant to interrupt behavior instantly and force retreat through chaos. From an evolutionary perspective, the design is brutally logical. Bullet ants defend fixed resources, nests at the base of trees, along roots or within buttress cavities that are essential to colony survival. They cannot flee with these structures. They cannot rely on camouflage. Instead, they turn contact into catastrophe. The venom contains peptides that hyperactivate pain receptors without causing significant tissue damage, ensuring that the message is loud, unmistakable, and memorable. Predators that brush against a nest do not learn slowly, they learn once. For humans, the problem is scale and context. One sting is debilitating. Several are catastrophic. Bullet ants do not sting in isolation when nests are disturbed. They swarm, each ant acting independently but collectively overwhelming. Multiple stings stack effects rapidly. Pain compounds rather than plateaus. The body responds as if under extreme stress. Heart rate spikes, sweating pours off in sheets, muscles tremble uncontrollably. Nausea follows as the nervous system struggles to maintain equilibrium. In some cases, people collapse, not because the venom shuts organs down, but because the system is overloaded by sensation and stress. This is where the clock angle emerges. Bullet ant venom does not kill through toxicity. It kills indirectly by stripping away the ability to make good choices in a hostile environment. Panic accelerates dehydration as sweating intensifies and breathing becomes shallow and rapid. Water intake stops. People stumble away blindly, desperate to escape the source of pain, ignoring footing, obstacles, and terrain. Falls happen on slopes slick with leaf litter or along riverbanks lined with roots and rocks. Ankles roll, heads strike branches. Secondary injuries stack on top of envenomation, turning a survivable encounter into a cascading emergency. The forest amplifies these risks. Amazonian terrain punishes loss of coordination. Trails are narrow. Edges drop into ravines or water, and visibility is limited by vegetation. A person shaking uncontrollably, eyes watering, muscles firing erratically, is a liability to themselves. The ants do not need to pursue. The damage is already propagating through the victim's own actions. Human scenarios repeat with grim consistency. Someone leans against a trunk to rest, unaware that a nest occupies the base. A vine is grabbed for support while crossing a muddy incline, hands closing around an ant highway invisible against dark bark. A step lands near a root flare where ants forage aggressively. Children playing around trees touch surfaces adults avoid instinctively. In each case, the trigger is not recklessness, but normal interaction with the forest. Bullet ants exploit the fact that humans rely on touch for balance and movement in dense environments. The physiological response to the sting reveals how finely tuned the venom is. Unlike venoms that cause necrosis or paralysis, bullet ant venom leaves tissue intact while forcing the nervous system into overdrive. Pain receptors fire continuously, overwhelming the brain's ability to filter signals. This sustained barrage explains why the pain is often described as unrelenting rather than sharp, a sensation that peaks quickly and then refuses to fade. The body enters a stress response loop, pumping adrenaline that keeps muscles tense and heart rate high, further exhausting the system. In hot, humid conditions, this leads rapidly to dehydration and electrolyte imbalance. From the ant's perspective, this is perfect. The intruder retreats, often violently, damaging nothing further. The colony expends minimal resources and suffers no structural harm. The venom dose is small, efficient, and metabolically cheap to produce compared to toxins that kill outright. Survival here is about deterrence, not elimination. The danger for humans lies in underestimating indirect effects. Many who survive bullet ant encounters do so without permanent injury, but the margin is thin. A fall into water during a pain-induced stumble can lead to drowning. A collapse far from shelter can expose someone to heat exhaustion or hypothermia during rainstorms. Dehydration worsens shock and delays recovery. Panic-driven decisions waste time and energy when calm, methodical withdrawal would minimize harm. The venom's true power is not in what it does to the body, but in what it makes the body do to itself. Indigenous cultures that live alongside bullet ants understand this intimately. Initiation rituals involving controlled exposure are not tests of toughness alone. They are lessons in composure. Enduring the sting without thrashing or collapsing demonstrates mastery over impulse, an understanding that survival depends on restraint as much as resilience. In the forest, pain is information, but not all information demands immediate, explosive response. This cultural framing highlights a biological truth often missed by outsiders. Stress responses evolved for short bursts of danger, not prolonged sensory assault in complex terrain. Bullet ants also illustrate a broader ecological principle. Social insects dominate tropical ecosystems not through size or speed, but through coordination and chemistry. Their success is built on turning small individual actions into overwhelming collective effects. A single ant is insignificant. A disturbed colony is a force that reshapes behavior across species boundaries. Birds avoid nesting near active colonies. Mammals alter foraging routes. Even large predators respect the boundaries defined by ant territories. Humans are latecomers to this system, and their pain tolerance is irrelevant to the ant's calculus. As the hours pass after an encounter, the sting sites throb and swell, but tissue heals. What lingers is exhaustion, dehydration, and sometimes injury from the aftermath, rather than the sting itself. The body recovers from venom faster than it recovers from falls, fractures, or heat stress. In this sense, bullet ants exemplify a form of ecological judo, using an opponent's own mass and momentum against them. The venom sets the stage. The environment delivers the follow-through. The lesson is not that bullet ants are uniquely cruel or dangerous. It is that in the rainforest, defenses are often designed to destabilize rather than destroy. Killing is expensive. Forcing an intruder to make catastrophic mistakes is efficient. The forest rewards strategies that shift risk onto others, letting gravity, heat, and terrain finish the work. When people say the bullet ant sting is the most painful in the world, they miss the point. Pain is not the end point. It is the opening move in a chain reaction that unfolds over minutes and hours, shaped by physiology and landscape. The ants do not need to kill you if they can make you ruin yourself. In that quiet efficiency lies their true power, and a stark reminder that in ecosystems this old and this crowded, survival often depends less on strength than on the ability to remain functional when everything inside you is screaming to fall apart. The bite is so small it barely qualifies as an injury. A pinprick, a fleeting itch, a raised dot that disappears beneath sweat and dust within minutes. In a forest that can crush bones, inject venom, or tear flesh in seconds, this seems almost insulting as a threat. Yet this is the most efficient wound in the ecosystem. It does not remove tissue. It does not announce itself with pain. It does not force an immediate decision. It inserts a needle, withdraws, and leaves you believing nothing happened. That is why mosquitoes run the longest clock of all. As daylight drains from the forest and the air thickens, movement becomes louder in a different way. Frogs call, birds settle, and the canopy traps heat radiating back from the ground. Human bodies stand out instantly. Every breath releases carbon dioxide in rhythmic pulses. Skin radiates warmth. Sweat carries lactic acid and other volatile compounds that disperse through still air like scent trails. To a mosquito, this is not background noise, it is a map. Tracking is not visual in the human sense, but chemical and thermal, a layered detection system tuned to find blood with astonishing speed. The approach is quiet and precise. A mosquito does not land randomly. It probes, tests airflow, samples the surface with sensory organs tuned to heat gradients and moisture. When it commits, the mouthparts assemble into a tool that looks fragile but functions like a surgical instrument. Multiple stylets slide together to pierce skin, bypassing nerve endings where possible, injecting saliva that prevents clotting and dulls sensation just enough to avoid detection. Blood flows. The insect feeds for seconds, not minutes, then lifts off lighter, already processing its meal into eggs that will repeat the cycle elsewhere. None of this is the danger. The feeding itself is trivial. What matters is what passes through that needle. Mosquitoes are not predators in the dramatic sense. They are vectors, bridges between bloodstreams, moving pathogens across species boundaries with ruthless efficiency. Viruses, parasites, and bacteria exploit the mosquito's life cycle, surviving inside its body and emerging in saliva during feeding. For the insect, this is incidental. For humans, it is transformative. The delay is the trick. After the bite, life continues. Work gets done at dusk when heat eases and mosquitoes are thickest. Fishing nets are checked, crops are harvested. People sleep without nets because the night feels calm, the air barely moving, the stars visible through gaps in the canopy. Children fall asleep uncovered, sweat-damp skin exposed. Nothing happens immediately. No collapse, no swelling, no urgent signal demanding action. The body absorbs the intrusion silently. Days later, the bill arrives. Pathogens introduced by mosquitoes operate on biological schedules that feel alien to human intuition. Viruses replicate quietly at first, hijacking cells without triggering alarms. Parasites migrate through tissues, completing stages of development before symptoms make sense. The immune system begins to respond only after populations reach thresholds that can no longer be hidden. Fever appears, headaches follow, joints ache, fatigue deepens into something heavier, more systemic. By the time people connect symptoms to a bite, the event itself is long forgotten, one of dozens or hundreds absorbed over the past week. This is why mosquitoes are so dangerous in environments like the Amazon. The forest is not hostile to humans by default. It is simply optimized for other life forms. Warm temperatures shorten pathogen incubation periods. High humidity extends mosquito lifespan. Standing water appears everywhere during rainy seasons, creating endless breeding sites that reset populations faster than control efforts can keep up. The ecosystem favors abundance and rapid turnover, conditions under which vector-borne diseases thrive. Human behavior aligns perfectly with mosquito opportunity. Dusk work coincides with peak feeding times. Sweat increases chemical signals that draw insects in. Carbon dioxide plumes intensify during physical labor. Sleeping without nets exposes the body for hours at a time, offering repeated feeding opportunities. Even attempts at comfort, rolling up sleeves, loosening clothing, expand the target area. The mosquito does not need to hunt aggressively. Humans advertise themselves constantly. The twist is not that mosquitoes kill, it is that they outsource the killing. The insect's evolutionary success lies in remaining insignificant enough to be ignored while carrying organisms that do the real damage later. From an ecological standpoint, this is elegant. The mosquito expends minimal energy, avoids confrontation, and remains largely unchallenged. Attempts to eliminate mosquitoes entirely often fail because they occupy so many niches and reproduce so quickly. They are woven into food webs, feeding fish, bats, birds, and insects, their populations rising and falling with rainfall and temperature. Fearmongering misses this complexity and leads to poor decisions. Mosquitoes are not evil, and panic does not reduce risk. What reduces risk is boring, repetitive prevention that clashes with human impatience. Nets, long sleeves. Repellents reapplied even when they feel unnecessary. Draining standing water. Screens, fans. These measures do not feel heroic. They do not produce stories of survival. They work precisely because they interrupt the mosquito's process before the clock ever starts. The difficulty is psychological. Humans are wired to respond to immediate threats. A snake bite demands action. A caiman attack triggers adrenaline and memory. A mosquito bite disappears into background noise. Prevention feels optional because consequences are delayed and probabilistic rather than immediate and guaranteed. This mismatch between cause and effect is where mosquitoes win. People skip nets once and feel fine. They forget repellent because nothing happened yesterday. The lesson learned is false safety. In the Amazon, communities that coexist longest with mosquitoes understand this dynamic intuitively. Prevention becomes routine, embedded in daily life rather than framed as emergency response. Nets are repaired as carefully as tools. Water containers are managed with attention. Clothing choices reflect insect pressure as much as heat. These habits do not eliminate risk, but they compress it, turning a constant threat into a manageable background factor. Biologically, the mosquito's role is a reminder that evolution rewards efficiency over drama. Teeth, venom, and claws are expensive. A needle and a passenger are cheaper. The smallest wound becomes the biggest clock because it shifts danger from the present to the future, from visible injury to internal process. You often feel fine today and pay later, sometimes days later, sometimes weeks, sometimes in ways that ripple through families and communities rather than ending with the individual. The forest does not care about fairness or narrative clarity. It operates on systems layered over systems, where outcomes emerge long after triggers have passed. Mosquitoes embody this better than almost any other organism. They are reminders that survival is not always about enduring the moment, but about managing what you cannot feel yet. In a place where life multiplies quickly and invisibly, the most dangerous encounter may be the one you barely notice at all. Night settles into the house the same way it settles into the forest, quietly, gradually, without ceremony. Tin roofs cool, wood contracts, insects take over the soundscape, and sleep arrives not as a switch, but as a drift. The walls feel solid, the ceiling feels distant. Nothing about a home suggests vulnerability. That assumption is exactly what bats exploit, not through intent, but through overlap. In the Amazon, the boundary between forest and shelter is porous, and the most dangerous encounters often begin when people are already unconscious. Above the rafters, in the dark seam where roof panels don't quite meet, a colony stirs. Bats roost in places that trap heat and stay dry, drawn to the same architectural features humans value for comfort. Gaps beneath tiles, attics filled with warm air, palm thatch roofs that breathe just enough to let insects in but rain out. These are not invasions. They are shared solutions to the same environmental pressures. The bats settle in, bodies packed together, heart rates slowing, metabolism dropping as they enter shallow rest cycles that conserve energy while remaining alert. Some species leave the roost to hunt insects, sweeping through the night air with echolocation pulses that map space in exquisite detail. Others, in certain regions, specialize in blood. Vampire bats do not swarm or attack, they select. Heat, carbon dioxide, and the slow rhythm of breathing guide them to sleeping mammals whose defenses are down. Their approach is surgical. They land lightly, test the surface with sensitive lips, and make a cut so small it barely qualifies as a wound. The saliva contains anticoagulants that keep blood flowing and anesthetic compounds that prevent the host from waking. Feeding takes minutes. Departure takes seconds. The sleeper rolls over, unaware that anything happened. The bite is often invisible by morning, a pinpoint mark, if it can be found at all, easily mistaken for a scratch or insect bite. There is no pain, no swelling, no blood-soaked sheets. This absence of drama is the most dangerous feature of the encounter. Humans are trained by experience to triage threats based on sensation and spectacle. Big wounds demand attention, small ones are dismissed. The bat's bite exploits that bias perfectly. The real clock begins when the bite is ignored. Certain pathogens carried by bats, including rabies viruses in some regions, do not cause immediate illness. They enter peripheral tissue quietly and begin a slow journey along nerves toward the central nervous system. This process takes time, days, weeks, sometimes longer, during which intervention can stop the disease entirely. Once symptoms appear, that window closes. Treatment shifts from prevention to palliation, and outcomes change accordingly. The bat does not deliver a fatal dose in the moment. It delivers a chance, and the danger lies in failing to recognize it. People dismiss bat exposures for understandable reasons. The mark is small. The encounter is hypothetical. There is no memory of being bitten, only the knowledge that bats were present somewhere above the ceiling. Seeking medical care feels excessive, even embarrassing, especially in remote communities where clinics are distant and resources limited. Life moves on, work resumes, days pass, the body feels fine. This reinforces the decision to do nothing, even as the only effective window for prevention narrows silently. Human scenarios repeat across the basin. Open homes without screens invite airflow and insects, and bats follow both. People sleep uncovered in the heat, skin exposed. Children nap during the day beneath rafters where bats roost. Grounded bats, found during daylight, are handled out of curiosity or concern, their presence interpreted as harmless confusion rather than potential illness. Attic cleanups stir roosts, startling animals that bite defensively when trapped against skin. In each case, contact is incidental, not malicious. The danger emerges not from the act itself, but from what happens afterward. Ecologically, bats are indispensable. They control insect populations that would otherwise explode, pollinate night-blooming plants, disperse seeds across vast distances, and shape forest regeneration patterns in ways that ripple outward for decades. Vampire bats, often vilified, are part of this same web. Their feeding behavior evolved to minimize harm to prey and maximize survival efficiency. Their saliva is so biochemically refined that it has inspired medical research into anticoagulants. The traits that make them successful are not accidents. They are solutions to the problem of living in dense, competitive ecosystems where energy efficiency matters more than force. The irony is sharp. The animals most associated with darkness and fear are, in reality, models of restraint. They do not tear flesh or kill outright. They take what they need and leave. The catastrophe, when it happens, is not the bite. It is the human failure to respond appropriately to something that feels too small to matter. Understanding bat biology reframes the horror. Rabies and similar pathogens are not designed to kill humans specifically. They are adapted to circulate within animal populations, moving through bites and saliva in environments where contact is frequent. Humans become involved only when they step into these cycles unknowingly. The disease's lethality is not aggression, it is incompatibility. Once the virus reaches the brain, the immune system cannot clear it without destroying the host itself. The tragedy lies in how preventable this is when exposure is recognized early. The Amazon's version of danger is often domestic rather than dramatic. It does not always announce itself with splashing water or snapping jaws. Sometimes it hums softly above your bed, hidden behind wood and thatch, part of the night's normal architecture. The house, meant to separate people from the forest, becomes another edge habitat where species overlap and rules blur. Safety becomes not a function of walls, but of awareness. Prevention here is unglamorous and absolute. Sealing gaps, using nets, avoiding direct contact with bats, alive or dead. Treating any unexplained bite or exposure as serious, regardless of how trivial it appears. These actions lack narrative punch, but they save lives precisely because they interrupt the clock before it matters. Once symptoms begin, there is no drama left to manage, only outcomes. The final lesson is unsettling because it inverts expectations. In the Amazon, the threat does not always come from what you see or feel. It can begin while you sleep, unnoticed, painless, forgettable. The forest does not always attack outside. Sometimes it starts the countdown above your bed, quiet and patient, waiting to see whether you will recognize that the smallest mark can carry the longest consequences.